Hi, welcome to Inside Out Math. This video is a second set of examples to iterated integrals, and in this video we're going to have to use a little bit of sense of geometry. So this first example here, actually our fourth example to the series, sketch the solid whose volume is given by the iterated integral and evaluate. Okay, so it looks like we're taking a double integral from 0 to 1, 0 to 1, of the multivariable function 2 minus x squared minus y squared dy dx. Okay, so first we'll sketch the solid, and it looks like this solid that we're sketching is, I'll call it f of xy equals z equals 2 minus x squared minus y squared. So this should be a little bit of review. You should have seen this in a previous section on how to graph this. We'll look at let's say the x trace first. Let's look at the x trace, and when we look at the x trace, we'll set x equal to 0. So we'll have the function z equals negative, 2 minus y squared. Okay, what we're doing here is we're projecting the solid onto the zy plane. Okay, we don't have to be too detailed here, but it looks like we have this is the z-axis and the y-axis. We have a vertical transition of 2 and a parabola that opens down. We'll notice how our bounds dy dx is from 0 to 1 and 0 to 1 in the y and x direction. So instead, I'm going to graph all the way until y equals 1. Okay, so my coordinate here is y equals 1, and z should equal, well, if y is 1, I do 2 minus 1 squared, which is 1, and so z equals 1 as well. And you can guess that this coordinate will be negative 1, 1. And on to the y trace. And for the y trace, we'll set y equal to 0. And we don't have to be too fancy here. Z x. Our graph is going to be z equals 2 minus x squared. Okay, so we pretty much have the same shape. Coordinate of 1, 1. Okay, we know what this point is here. And for the z trace, we'll let z equal k or z equal 0. I think in this case, we'll project it onto the xy plane. We'll set z equals 0. So we'll have adding x squared and y squared to both sides of the equation, we'll have x squared plus y squared equal 2. So we have a circle of radius 2 on the xy plane with radius root 2. This is y and x. So let's put everything we know together. Scroll down here. X, Y, Z. That's not a very good X. X. Okay. We know that in the XZ plane, let's say this is 2 here, we know that it'll range this way until x equals 1. And in the ZY plane, we have that parabola that until y equals 1, so z equals 1. And connecting all the dots here, looks like we'll have some paraboloid. Oops. That's better. Okay. And it looks like we're just trying to find the volume of the inside of the solid. We'll go ahead and evaluate the double integral. Double integral from 0 to 1, 0 to 1 of 2 minus x squared minus y squared dy dx. Okay, evaluate with respect to y first. So we'll get the integral from 0 to 1 of 2y minus x squared y minus y cubed over 3. Again, this is just calculus 2 material here, just taking antiderivative. So I'll go through it fairly quickly. 0 to 1. Plug in our limits of integration here. We'll plug in a 1, so we'll have a 2 minus x squared minus 1/3. Plug in zeros, we get a bunch of zeros here. So we're left with this integral with respect to x. Evaluate as it is from 0 to 1. It'll be 2x minus x cubed over 3 minus a 1/3 x. And that'll be evaluated from 0 to 1. And we'll get a 2 minus 1/3 minus 1/3. And we're left with 2 minus 2/3 is 1 1/3, which will come out to 4/3. This is our solution. Okay, and on to the fifth example. Find the volume of the solid in the first octant bounded by the cylinder z equals 16 minus x squared, and the plane will cut off the cylinder at y equals 5. Okay, so let's go ahead and just graph this first. Boom. Boom. Oh, come on. Bam. Let's go ahead and construct our axes. Do it in y. X, Y, and Z. Alright, and do that too. Okay, so it looks like on the ZX plane, this ZX plane here will have it's a radius of 4. Okay, and of course this plane that cuts off the cylinder, as you can see, this will be again y equals 5. Okay, so it looks like we have this rectangular domain in the xy plane. Okay, we can use Fubini's theorem, and let's go ahead and set up the integral. Looks like we're evaluating 16 minus x squared, the solid, and we can do dx dy, or we can do dy dx. You're free to do whatever you'd like because of Fubini's theorem, integrating over a rectangular region. Okay, let's just do dy dx. So if we do dy first, we'll evaluate the y from 0 to 5, and of course in the x direction we're only going from 0 to 4. Okay, antiderivative to 16 minus x squared with respect to y becomes the integral from 0 to 4 of 16y minus x squared y, and we'll evaluate this from 0 to 5 dx, and plugging in our bounds here we'll get I guess 16 times 5, I'm not sure what that is, minus 5x squared, I should say. It's an integral from 0 to 4 dx. Okay, 16 times 5, antiderivative is 16 multiplied by 5 times x. I'm a little bit lazy right now. Minus 5x cubed over 3, evaluated from 0 to 4, and we'll get 16 times 5 times 4, whatever that is, minus 4 cubed is, I believe, 81. 5 times 81 over 3. Let me think about that one more time. 16, 4, 16, oh, that should be 64. I'm sorry. 5 times 64 divided by 3, and this should be your answer. I don't have a calculator on me again, so. I'll go 16 times 5 times 4 minus 185 times 64 divided by 3, and I get, okay, the answer is 640 over 3 equals 640 divided by 3. There we are. Thank you for watching, and have a great day.